Hey guys, um, today I found a interesting problem that came from the daily codings. I found this problem interesting because first of all, I love graph. It's a graph problem, and you need to use multiple data structure. That's another helpful or good things to practice with. So let's see what is the problem about. I'm not going to read the whole problem because I already, of course, read multiple times. You can read by yourself for sure. So let me put it in a different line. Okay. So what is the problem is saying that a graph has been represented by an adjacency list. Okay. And from that graph, you have to go to the transitive closure of this graph. What is the transitive closure means? It means that every single node you have to find that every single node that other node is reachable or not. If it is reachable, you mark it as 1. If it is not, it is 0. So let's start with an example. Let's build this graph first, that how the graph look like, and then we will go from there. So the graph is saying here that the node, so since an adjacency list, how the adjacency list work? So this one is like your index 0, 0, 1, 2, 3, and then this is the next first index and the second index, etc. So this 0th index means the node 0. So let's draw a node. So this is the 0 node, and the 0 node is of course connected with itself, right? Which is fine. And then it has two other node, 1 and 3. So let's draw 1 and 3, right? So I'm going to draw here is 3, and then here would be 1. So 1 and 3 it is connected. Go to the next node. The next node is of course connected with itself because 1 is connected with 1, and then it's connected with 2. So we don't have that node. Let's create that node. So here, and it is connected here. Let's make it it has a direction. Okay, and then the next one is 2. That means the 2 is connected with itself, which is fine. And then next one, the last one is 3, and it is also connected with itself. So this is the graph it looks like, right? Now from this graph, first of all, we have to create a adjacency matrix. So what can we do? It has 4 nodes, so let's create a 4 by 4 matrix. 1, 2, 3, and 4, and then 1, 2, 3, and then 4. Okay, so it's a 4 by 4 matrix. Let's draw that. Now we can mark his a different color. So let's say this is the 0th column, this is the first column, this is the second column, this is the third column. And in the row wise, this is the first row, 0th row, and the first row, and then second row, and then the third row. Okay, so if you see the input in the adjacency list, that 0 is connected with 0, so we can say mark as 1, and 0 is connected with also 1, so here, and 0 is connected with 3. 0 is not connected with directly 2, as you can see, right? But we have to find out. Okay, and then 1 is connected with itself, which is 1, and it also connected with 2. But what happened? All other nodes is 0, 0. Okay, now 2 is only connected with 2, right? So you cannot reach to any other node, but we have to find out. And 3 is connected with 3 itself. Okay, now let's see when the question says that you have to find what? You have to find the transitive closure, meaning that from 0th node, what other node you can reach. 0 to 1 is possible, right? And 0 to 2, is it possible? It looks like is 0 to 2, I can come to 1 and I can come to 2. So it is possible. If it is possible, I have to just mark it as 1, right? So let's take red. So I mark it as 1. So it is possible. Is it 0 to 3 is possible? Yes, possible. Now go to the next one. From 1, where you can go? From 1 to 2 and 1 to 1. Other than that, is there anything you can go? Can you go to 1 to 3? No, because the direction is different. And same case for 2. Can you go anywhere else? No, you can go from 2 to 1 because it's not the opposite direction. And you can go from 2 to 3 because the same path, it's the opposite direction. So basically from every node, you have to find out that what other node you can reach, and you have to update this matrix. That's what it means. So now if you think about the easier approach or the naive approach, what you can do that first you can take this node 0 and you can check that what are the node you can reach, and then you can take 1 and you can check what are the nodes you can reach, and you can take 2, what are the node you can reach. So although this is a naive or the brute force approach, but you can exactly do that. It's a brute force is you can use here. And the similar algorithm for this kind of problem, that for every vertex to reach all other vertices like in a shortest distance or the shortest path, the algorithm we use called Floyd Warshall. So although Floyd Warshall is used to find the shortest distance from one source to all other vertex, you can use the same algorithm here. Instead of finding the distance, we are just checking that is it possible to reach. So that's easy, right? Okay, so what is Floyd Warshall does? What is that algorithm? Let's talk about it, right? Let's make another graph and talk about it. So let's say you have a node here, which is 1, and then let's say there is 3 other node, right? Okay, so what Floyd and Warshall does is, he said that, okay, well, you take a node like this one, 1, can you reach to 2, right? It's clear that yes, you can reach to 2. And then he asked that, can you reach to 2 from 1 by using other node? What it means, that can you reach to 2 by using other node like 3 and 4? Can you do that? You can come to 3, there is no path. You can come to 4, you cannot reach there, right? So it is not possible. And the same question, 1 to 3, yeah, you can reach, but can you reach from 1 to 3 by using as a station? Think about like a station that you want to come from 1 to 3 by through this node or this city 2. Can you do that? No. So let's make some other node. If I do this, now I can ask that 1 to 3 is possible. Can I go from 1 to 3 by using other node 2? It looks like yes, I can do that. What is the path? 1 to 2, 2 to 3. So basically I have to come from 1 to 2. First I have to come from 1 to 2, and then I have to go from 2 to 3, right? Remember that this 2-piece information is very important. Okay, and now you can come from 1 to 4, but is there any other way? Can I come from 1 to 4 in a different node, right? If there is another node or even a 3 would be like this. Can I do that? Yeah, I can come from 1 to 3 first. I can come from 1 to 3 and then 3 to 4. So these information or this style will be important for Floyd and Warshall. So basically what we are doing, we take a source, we go to the destination and we check that is there any other way I can go from source to destination. That's simple as that, right? Okay, so we will be using this logic to implement this. But before that, we have to implement that adjacency list and the graph and this matrix. So let's build one by one, okay? So I'm going to move it out on a different screen. All right, we will bring it back whenever we need it, okay? So let's start. We have to first create a graph. How to create a graph? Like this. It's a graph, integer, and I also name it as a graph, okay? New array list. What is the size? It depends on the number of nodes. So let's say the number of nodes is n, and what is that n for our example? N is 4 because 0, 1, 2, 3, 4. It's a 0 indexed. So this is how it works. Okay, what is going on here? Okay, new list. Okay, so because it has to be an array. Okay, now it's good. Now each of these node has to have that list of child, right? Meaning that how that looks like. 0 will have list of items like 1, 3, and of course 0 itself. See? So for this first position, it has to have a list of items. Second position, such as this, right? What it has, 1 and 2, right? So another list. So we need to clear that. So let's do that. Right? And come here. graph, we are just initializing. Okay, yeah, new list, right? We are not putting anything. It's fine. Okay, now let's build that graph. That in that case, first node, this is the first node, you get a list and then add 0, right? The first node is 0, and then whatever the second node, let's do that. What is the third one? So basically the first node has 1 and 3, right? So let's do that. 1, and this one is 3. Okay, cool. Now come to the next node. What is the next node? Next node is 1. Okay, so 1 is what? Next node is 1. 1 is connected with 1 itself, and then 2. Okay, go to the next node. What is the next node? 2 and 3. Okay, next node is 2. 2 is connected with what? 2 is connected with 2, and then the last one is 3 is connected with 3. Make sense? All right, so we have this graph, right? Has been built, which looks good. What we could do, probably, I have a master printer. Let me see if it has, I think. Okay, so yeah, so if we do that and pass the graph, let's see how that matrix looks like. Okay, so never mind, there was a mistake. The mistake was this shouldn't be the 2, it should be actually 1, because there is no 2, only 0 and 1 binary matrix. Okay, sorry about that. So the graph, as you see, the 0 is connected to 0 1 2 or 1 3, and 1 is 1 2, and then 2 2 and 3 3. So our graph is ready. Now we have to find what? The transitive closure. So let's do that. Oh, before that, our result is an adjacency matrix, right? So let's say matrix. What is the matrix size? Of course, n by n. Okay, so which is cool. Now, before even updating or the finding its transitive closure, what we could do probably that we can pre-populate it. Like literally, we are converting this adjacency list or the graph into a adjacency matrix. What can you do about it, or how can you do that? So let's do that. We have to go through each of these nodes, right? So integer, those are the child of graph, and then as I. So each node, from the node you basically get the list, and when you have all those child, you go about those child. I'll say C as a child. Probably we can do better, make it easier. We'll say integer C, so it will give us the each child. Now what we are going to do, matrix I and then C equal to 1. So what will happen is that this matrix will be that the graph we represented with adjacency list, now it will convert it into adjacency matrix. So let's print it. I have a master printer. Print matrix, right? If it's a matrix, run it and look how that looks like. Okay, look at this. The first 0 and 0 was connected, 0 and 1, and 0 and 3, and then 1 and 1, 1 and 2, and then 2 and 2, 3 3. So literally what we did here is that our adjacency list we converted into an adjacency matrix. Now is the time to find that transitive closure. So let's make a call, find transitive closure, right? What do you pass? You pass that matrix. All right, and then the size. That should be good enough. Let's do that. Okay, so we need here is 3 loop. This is the interim intr interim node, that what we talk about, that from source to destination through this interim node, right? Okay, let's make it into, oops, okay, that's fine. Okay, now this is called source, size again node, because each of this node, and then another one we'll call it destination, right? Okay, so for each of these already, if the matrix value, because maybe it's already possible, right? What can you do about it? Matrix source and then dest destination is equal 1, we don't need to do anything. Okay. Okay, and then if now will be that we will go from source to interim node and interim node to destination node, and both has to be 1. If source to interim node is not possible, then there is no way that you can go to the destination with this interim node. So what you do is matrix source to interim, right? intr interim node is equal 1. So it is possible from source to interim. Now what happened interim node to destination? Matrix intr interim node to destination. If that is also 1, you say that okay, maybe in that case source to destination is possible. Dst destination and source is possible. You just update that. Okay, that's simple as that. The time complexity, it will be higher. Why? Because you take each of these vertices and you iterate over all others, right? So the time complexity would be big O of n and cube. N here, n is the number of vertices, right? Whatever with the space, because in the space wise you created an adjacency list and then you have the matrix. So the matrix space complexity, the matrix itself is take n time n, okay, and you have an extra m for the adjacency list, but the worst case is this. Okay, so let's print it how that matrix looks like now, right? We can print it very easily. Let's do that. Master printer dot print matrix. Okay, all right, hope that works. All right, see, it works, right? This is the result we are looking for, and we are going to run through few other example of the graph to verify that how that looks like. Let's take a star graph. Okay, I have an example. I'm going to take it. Okay, so this is our star graph, right? In that star graph only you can reach from 0 to 1, 0 to 2, 0 to 3 and 0 to 0, of course. Basically you can take this above so that it will be better organized and more easier to understand. Let's run it. Look at that, you can reach from 0 to 1, 0 to 2 and etc., but there is no other possible way. How is that? So let's go to that, make a star graph here, right? Let's draw a star graph. I'm gonna take my favorite color, right? Okay, so there is 1, which is your 0th node, and then you can reach to 1, you can reach to 2, and you can reach to 3. But from 1 to 2, is it possible? No, because the direction 3 to 2, 2 to 3, nothing is possible, right? So it's kind of a star graph. You can have many other nodes, right? Okay, let's take in another example. That will be a different structure as well. So I have a copy. I'm gonna take that. So let's select that. I can run those as a unit test, but try to make it simpler. Okay, so now in this graph 0 to 1 is possible, 1 to 2 is possible, 2 to 3 is possible, 3 to 4 is possible. So how that graph look like, right? That graph is basically looks like this. This is the 0th node. You can come to 0 to 1, possible, and then 1 to 2, right, that is also possible, and then 2 to 3 possible, and 3 to 0 again, it's possible. So basically you can reach from each node to every other node. From 2 you can go to 3, you can go to 0, you can go to 1, and again 1 to 2, 2 to 3, any other nodes. So let's run that, how that looks like. Voila, it works, right? You can reach from any places to any other place. So that was a fun. We learned that Floyd Warshall, and then adjacency list data structure, and how to represent a graph, and then how to create a 2D matrix. So multiple data structure involved here, right? That was cool. Yeah, thank you. Hope you guys enjoy.